Okay, before we go on, I just want to review this problem again very briefly because it's going to help us with the next problems. Remember that, first of all, obviously this is our vertex. Okay. Now, the next question is, what about increasing and decreasing regions? Increasing means as we go from left to right. So we increase as we go from left to right. Okay, so that would be along the function like this. We're increasing in this region. Okay, so for example, let me just change colors a little bit here. At the point, let's say negative, at x value of -5, is that part of an increasing or decreasing region? Well, if I go to the function, at that point, I'm going to hit the function right about here. That's part of a region that's increasing from left to right. So this would be part of an increasing interval. How about -8? Same idea. If I go way down here, the function's increasing at that point. Okay? In fact, all of this is increasing. All of these x values are part of a region of x values corresponding to points on the graph where the function's increasing from left to right. So how do we label this interval of x values? We label it starting at -infinity and ending at -1. Now, the next question is, do I include -infinity? Well, no, because you can't get to -infinity. That's why it's infinite. So we put a round bracket because we can't get there. Do I include -1? Well, no, because at -1 itself, you're not increasing or decreasing. You're stationary at that point, kind of like the top of a roller coaster. And so I don't include it. I stop just before it. So we use a round bracket to indicate that. Okay, so that's my increasing interval right here. Okay, -infinity through -1. Now, what about decreasing? Well, for decreasing, again, that's decreasing means as we go from left to right. So are we going downwards as we go from left to right along the graph? And the answer is this region of the graph right here. That's a decreasing region of the graph, but we label the region based on the x values of those points. So for example, x equals 2. That's part of a decreasing region of the graph. What about x equals 4? Well, if I kind of go to x equals 4 and kind of go down to the graph, which would be way down here, I'd hit the graph right here, which is, again, part of a decreasing region. So that would be part of a decreasing interval. In fact, all of these x values correspond to points on the graph where the function's decreasing. So that decreasing interval would start at -1 on the left, right here, and end at infinity, way out here. Okay? Now, the next question is, what about the endpoints? Well, infinity always has a rounded endpoint because you can't get there. In this case, -1 is also a rounded endpoint because at -1 you're not increasing or decreasing. Okay? I just want to kind of remind you guys of these properties before we move on. Okay, so now let's move on to the next problem. Okay, hang on one second. Okay, so now let's go on to problem 14 and use what we've learned to solve this. So first of all, to graph this function, we should follow the previous steps to graph it. So when they say graph this, what do they mean? Well, first of all, where's the vertex? What's the A, B, and C? Okay, my A is 2. What's my B? Notice there's 0 x's here, so my B is 0. What's my C? C is -4. Okay, so what's my vertex going to be? The x of the vertex is going to be -b over 2a, which is 0 over 4, which is 0. Okay. What about the y of the vertex? Again, we plug the x in. Okay, so n of 0. Plug the x into the function. N is the name of the function. So we plug that in. We're going to get 2 times 0 squared minus 4. In this case, it's -4. Okay, so my vertex is going to be at the point 0, -4. Now, another way to see this is just look at the transformations involved. If I start off with x squared, so here's a graph of x squared. All right, this is just y equals x squared. If I then multiply by 2, a multiplication just makes the function taller and skinnier. Okay, it doubles the height. So all the heights go double. So there's 2x squared. And then if I subtract 4 from the function, I'm going to move it down by 4. Okay, and hit a height of -4 here. So notice that this point is at the coordinate 0, -4. So we can also deduce where the vertex is thinking about transformations. That's possible because there's no x term. When there's no x term, it's easy to spot the vertex just by thinking about the transformations. When there is an x term in there, it's a little more difficult, and it's easier to use this ABC method and use negative b over 2a. Okay? But in either case, we found the vertex, 0, negative 4. Now, is the parabola opening upwards or downwards? Well, remember, the x squared term basically controls the behavior because it's the biggest power. And if there's a positive in the front, we go up. If there's a negative, we go down. So obviously we're going up. Okay? Can we find the x-intercepts? To graph it, we need to know the x-intercepts. Why? Because we have to know how wide the function is, how wide the parabola is. So for x-intercepts, we make the y equal to 0, right? So that means we make the function equal to 0. So in this case, when there's no x's, we don't have to bother factoring. It's kind of easy. We can just isolate the x squared and then take square roots. Okay, so I'm going to have 2x squared equals 4. X squared equals 2, dividing both sides by 2. So x equals plus or minus root 2. All right, that should be plus minus. I can't really write 2 out the bottom of the pen pad. So that's a plus minus root 2. Root 2 is about 1.4. Okay, so about here and about here. So it's a fairly tall, skinny parabola. Okay, and we already know the y-intercept because when we make x, so for the y-intercept, we make x equal to 0. And so if I make x equal to 0, we just plug that in. So we're going to have 2 times 0 squared minus 4 is negative 4. But we already knew that because I already see the function crossing the y-axis there. Okay, so here's what my function is going to look like. Again, I'm not the world's best artist. Maybe only the second or third best, right? Okay, all right, maybe the fourth best because, yeah, Picasso, he was all right. Okay, now, so there's our function. Now, what about increasing, decreasing? Remember, increasing and decreasing always means as we go from left to right. So as we go from left to right, where are we going upwards? We're going upwards here. But again, what are the x values for that region? That's what they're asking us for in this location. So you should be able to do that now. What are those x values? Okay. What about decreasing? Decreasing is going down as we go from left to right. Okay, what are those x values? That's what we're asking for. Make sure to understand whether we use rounded or square brackets on the endpoints. Okay, if you're not sure about that, back up to the previous problem to go over that. Okay, maximum and minimum. Okay, do we have a maximum? Is there an overall highest point? Remember, this function goes up forever. Okay, if there is no overall highest point, we would say D and E in both boxes. Okay, what about a minimum? Is there an overall lowest point, and where does it occur? What about domain and range? Domain is a set of x values, and remember, watch the previous video if you're not sure about this, but the domain is a set of x's where if you pick an x and you go up or down, you'll eventually hit the function somewhere. So I go up or down on this x, I'm going to hit the function, so that's in my domain. What about this x right here? If I go up high enough, far enough, I'll eventually hit the function, so that's in my domain. Okay, so think about what the domain would be. What about the range? The range is a set of y values where if you go across left or right, you'll hit the function. Okay, so if I pick, for instance, 1, is that in my range? If I go across, bing, I actually hit it twice, bing, that's okay, that's in my range. If I go to 7, bing, bing, that's in my range. If I go to negative 4, bing, I hit it. What if I go to negative 5? Ruh-roh, right? Ruh-roh. Who am I quoting? Famous movie quote or TV quote? Scooby-Doo, right? One of our most famous actors, right? I miss it. Ruh-roh. Ruh-roh. I'm not hitting the function, so these are not in my range. Okay? Now, when you write out the range, think about square bracket versus round bracket. Do you actually reach the particular height that you're placing at the endpoint of the range? If you do reach that height, you have to use a square bracket. If you stop just before that height, then you use a round bracket. Okay, and we went over this in a previous problem. So you can watch part 1 if you're not sure. Now, also remember that to solve this, we need to know the vertex. Basically, once I knew the vertex, the problem was done. Once you know the vertex, well, actually the vertex really, and whether it's opening upwards or downwards, and you're basically done. I mean, except for the graphing. For the graphing, we also really want to also know the x-intercepts and y-intercepts. Okay, so the x-intercepts and y-intercepts help us with the graphing, but in terms of increasing and decreasing, once I know the vertex and whether we're going up or down, I can spot what's happening. All right? Okay, so you should be able to do this one. This one should be easy for you. If it's not easy, rewatch part one. You're going to have to do this on the final, so make sure, rewatch part one if this was not easy. Okay? All right. Okay, so in this particular problem, number 15, again, we have a quadratic function, but in this case, it's an application problem. So the output of this function represents the height of the object, and the t is, of course, the time since the object's been traveling. Okay, so our output is the height. Okay, whoops, let me turn my pen on. Okay, so my output is the height. So the output here represents the height of the object. Okay, and this is my time, t. And so when they say when will the object be 68 feet of height, that means that's an output value, not an input value, because it's a height. Okay, so that means we have, let me change colors here a little bit. That means we have 68 is equal to negative 16t squared plus 122t plus 14. Okay, now, can we try factoring the function at this point? And the answer is, well, no. I mean, we could. There's no law against factoring it, but it won't help us solve the problem. Why? Because we don't have 0 on the other side. We cannot, basically, if I give you two mystery quantities, I just say I've got two things, I don't know what they are, but I know they multiply to 0. Can you tell me what they are? And the answer is one or both have to be 0, right? But what if I tell you I've got two mystery quantities, I don't know, and another I don't know, and they multiply, I don't know, to 68. What are they? Well, it could be a 34 and a 2, right? It could be a 17 and a 4. It could be a 68 and a 1. It could be a 136 and a 1/2. Okay. It could be a negative 17 and a negative 4. It could be a negative 68 times a negative 1. It could be a negative 136 times a negative 1/2. It could be a negative 34 times a negative 2. How many ways could two mystery quantities multiply and give you a 68? I could go on forever. How many ways can two mystery quantities multiply and give me a 0? Answer, just one way. You have to use a 0. 0 is the only number with that property. Okay? So the only way to solve when you have a polynomial, meaning a function with positive, whole number powers on the variable like this is a quadratic, which is a type of polynomial, and we want to find the value of x, or t in this case, that makes the equation true, we have to do it with 0 on the other side. Okay, otherwise factoring will not help us. So I need to get a 0 on the left side. I have to be able to use this property. Okay, let me change colors here. Actually, I want to be able to use this property. Okay, so how do I do that? I need to get the 68 away. I need a 0. Okay, so I'm going to minus 68 on both sides. Bada bing, bada boom, right? So I'm going to have 0 equals negative 16t squared plus 122t, and then what does 14 take away 68? Negative 54, right? Okay, so how do I solve that? Well, I could try possibly factoring it, but these are pretty big numbers. It might be difficult to factor. Can I factor some common, is there like a greatest common factor I could factor out of all the terms? Well, I can't factor t out of all the terms because I don't have any t in that third term, but I could at least factor a 2 out, couldn't I? Let's try factoring out a 2 and see what we get. Okay, so if I factor out a 2, and actually I don't like a negative at the beginning, so what if I factor out a negative 2? Can I factor out a negative 2? What do I end up with? Negative 16 divided by negative 2 is is positive 8, my bad. Okay, so positive 8t squared. 122 divided by negative 2 is what? 61, but negative 61. Right, because negative 61 times negative 2 gives you positive 122. And then negative 54 divided by negative 2 is what? Positive 27. Okay. Now, did this help me? Well, it made the number smaller, which is good. Okay. I still don't want to try factoring this by hand. It's going to be difficult, but what can I do with that negative 2? Well, we can divide both sides by it, right? You're allowed to divide both sides by the same thing as long as what you're dividing by is only multiplying. You can't get rid of things that are adding or subtracting by division, but if it's purely multiplying, I can divide. Okay, so that cancels. 0 over negative 2 is still 0. Okay, so I have 0 equals 8t squared minus 61t, that's a t, sorry, plus 27. Okay, now how do I solve that? Well, in this case, it looks difficult to factor, so we're going to have to resort to quadratic formula. Okay, what does quadratic formula say? It says that the value of t or x or whatever your variable is that makes a quadratic equation true, as long as the quadratic equation is set equal to 0, is a kind of an unusual combination of the a, the b, and the c coefficient. My a is 8. Okay. My b is negative 61. My c is positive 27 in this case. Okay, and so the x that makes this true is going to be, and it's kind of an unusual combination, x equals the negative of the b coefficient, and then either plus or minus, both will work, square root of the b coefficient squared minus 4 times the a times the c, whole thing, in both terms, including the negative b, all divided by 2a. Notice the negative b over 2a part right here is the formula for the x value of the vertex. So what we're saying is go to the x value of the vertex and then either add this unusual amount or subtract this unusual amount to get to the x-intercepts. Okay? Now, let's go ahead and plug in numbers. Excuse me. So in this case, I'm going to have the negative of negative 61 plus or minus square root of negative 61 squared. So these are kind of ugly numbers here. Whoops, negative 61 squared. Sorry about that. Minus 4 times, we're kind of running out of room here, times the a, and let's see, my a is 8, and my c is 27. Whoops, I guess I'm running out of room. Let me start it here. So it's the negative of the b. Okay, so negative of negative 61 plus or minus square root of b squared minus 4 times the a, which is 8, times the c, which is 27, whole thing divided by 2a. Okay, so it's a lot of work. Okay, it's kind of annoying, but it is what it is. Okay, so let's keep going with this. So I'm going to have 60, negative on the negative is positive, so we're going to have 61 plus or minus, and let me go ahead and grab my calculator here, see what we get inside that root. Okay, so 61 squared, whoops, I grabbed my phone instead of my calculator, one of those days. Okay, so I'm going to have negative 61 squared minus 4 times the 8 times the 27. So I'm getting 2857 in that root, all divided by 16. Okay, now what is the root of 2857? Well, it's not a whole number, but it's a decimal. It's 53.45 roughly. So I'm going to put approximately now because we're approximating. 61 plus or minus about 53.45. That's a 5 there. All divided by 16. So if I split that into two cases, I'm going to have either 61 plus 53.45 over 16, or I'm going to have 61 minus the 53.45. 61 minus 53.45 over 16, and I'm going to get a decimal for each of those. Okay, so let's do the minus one first. So I'm going to do 61 minus that number, and then divide by 16, and I get about 0.47 roughly, 0.4718, but to two decimal places about 0.47. Okay, so 0.47. Okay, so that is a time when we throw the ball up in the air, or the object, and it, by a machine, okay, it's tossed up, and it reaches the height of 68 feet at that time. That's the number of seconds. Okay. Now, what about the other value? 61 plus that number. So 61 plus the 53.45. divide by 16, and I'm getting about 7.15. So over here we're getting about 7.15 seconds. So again, we're not getting whole numbers in this case, we're getting decimal approximations, but that's okay. All right, so that answers our question. But again, the idea is we're doing application problems now with quadratics. All right, let's try another application. Actually, I just noticed there's a second question here that for some reason I didn't put into the slide. The second question says, how long till the object reaches the ground? So let me pop that in there. Sorry about that. So when it reaches the ground, that means what's the height? If something reaches the ground, that means the height is 0. So if it reaches the ground, that means my h is 0. So in this case, I again have a quadratic, but in this case, I don't have to move anything around to get 0 on the left. It already is a 0. Okay? So can I solve this? How would I solve this? Well, we can factor out a greatest common factor. It looks like a 2 factors out of all the terms, but I'm going to factor it out as a -2 so that I don't have a leading negative. So I'm factoring a -2 out of all the terms. What do I get? -16 divided by -2 is what? +8. 122 divided by -2 is what? -61. Negative times negative gives you positive. And this is going to be what? -7. -7 times -2 gives you +14, right? Now, I can then divide away the -2 on both sides because we're allowed to divide both sides by the same number. And this will cancel. Why am I allowed to cancel those -2's? Because it's only multiplying. If it was adding or subtracting to something else, I would not be able to cancel it. Like, for instance, could I cancel this 8? Could I divide both sides by 8 and get rid of that 8? No, because it's adding or subtracting to something else, okay? But the -2, I can divide and cancel it because it's only multiplying, okay? So I end up with the new quadratic. What's the new quadratic? 0 equals 8t squared minus 61t minus 7. Now, I don't want to try solving that by factoring. It looks difficult to factor it by hand, but we would then use quadratic formula. Okay, now in this particular instance, if you want to practice quadratic formula, you should get t equals 7.74 seconds to 2 decimal places in this example. So if you want to go ahead and practice your quadratic formula there. All right, do you need to memorize the quadratic formula for the test? I can't recall if it's on the formula sheet or not, but it's something that you should just know. It's just part of life. If you're moving on to other math classes, you have to know the quadratic formula. Okay? All right. So now let's go on. Okay, so in this case, again, another application problem, and we're going to end up with a quadratic. So applications of quadratics. So how do we find the area of a rectangle? Length times width, right? The area of a rectangle is length times width. But let's call this x, I guess, for the length, kind of in the horizontal direction. We'll call this guy y, right? Y and y, right? They're both the same. And so in this case, length times width would be the x times the y. Okay? Now, here's the problem. We've never seen functions that have 2 variables in them. So my area has 2 variables. But we really, to find a graph of something, we just want 1 variable, 1 input. So what I need to do is I need to write 1 variable in terms of the other. And the way we do this is essentially we use the other information. I mean, right now, one way to find the maximum area would be just make x like 1,000,000 and make y like 1,000,000,000. That would give me a nice big garden, wouldn't it? Like 1,000,000 feet by 1,000,000,000 feet. How about 1,000,000,000 feet by 1,000,000,000 feet? That's even better. In other words, right now, I could just make both variables as big as I want and get a huge area. So what we have here is we have what's called a constraint. So this quantity right here constrains my choices. We only have 800 feet of fencing. That's called a constraint. When we have optimization problems where we're trying to find the biggest or smallest of something, we typically need to have a constraint so that we don't pick just arbitrarily huge numbers or arbitrarily small numbers. Okay? So what does that constraint say? It says that I have 800 feet of fencing. Now I have to fence this side, and this side. So that means a y for this side, plus an x for this side, plus another y for this side, all has to be 800 feet. That's how much fencing I have. Okay, I don't have to fence the top side because that's against the river. All right, so that means 2y plus x is 800. So that's my constraint. We want to incorporate that constraint into this function that we're trying to maximize, and that will help us to, it'll first of all eliminate a letter, and secondly, it will make sure that we're not picking arbitrarily big numbers. So the way to do this is take your constraint and solve for one variable, whichever one's easier. Solve for one variable. In this case, it looks like the x is easier to solve for. So I'm just going to subtract 2y from both sides. Okay, and I end up with what? I end up with x equals 800, take away 2y. So what we're going to do with that 800 minus 2y is that can take the role of x. That can take the place of x. So I'm going to plug it in for x right here. So once I do that, I'm getting what's called a constrained objective function. I'm constraining my objective. So in my new area function is going to be, instead of x, I'm going to use what I found x to be based on the constraint. 800 take away 2y, okay, times the height or width of the garden, okay, and of course I can distribute this y into both terms. So I have area is what? 800y minus 2y squared. That's a quadratic because as an x squared, we'll actually have y squared, but it's a quadratic. We typically like the higher powers first, so I can put the negative 2y squared first, and then the y's. Just keep the sign with the term, negative on the 2, positive on the 800. Okay, when we switch them around, so again, we've got a quadratic. Right here, this is a quadratic. Okay, now, next question is, we want to find the maximum or minimum. Now, with this quadratic, so a quadratic will graph as a parabola, and a parabola will have a vertex, right? Now, is this parabola opening upwards or downwards? This is a downward parabola because there's a negative on the leading coefficient. So it's a downward parabola, which means that the vertex will be the maximum. So if you want to find the maximum area, which is what this equation represents, we need to find the vertex. Okay, the vertex will represent the maximum because it's a downward parabola. How do you find the vertex? Vertex is going to be at where? X equals, so for my vertex, x is going to, or in this case it's not x that we're solving for, it's y, but your variable for your vertex is going to equal what? The negative of the b coefficient over 2 times the a. So what are my a, b, and c? Well, my a coefficient is negative 2, my b coefficient is 800, and my c coefficient is 0, because I'm not adding any constant numbers by themselves. Okay, so let's go ahead and work this out. So I have negative b over 2a, so negative of 800 over 2 times negative 2, so that's negative 800 over negative 4, which is what? 200. So 200 is your y. So my y is 200. Now how do I get the x? So that means this dimension right here is 200 feet. What about the x? How do you find the x? From the constraint. Here's my constraint. The constraint relates the two variables to each other. We've already actually isolated the x within the constraint. So when you isolate a variable within your constraint, that's the best place to look to solve for the other letter. Okay, so once I have my y, I can plug it in right there. So this is going to mean my x is 800 minus 2 times the y, but the y was 200. Okay, so I've got 800 minus 400, which is kind of like about 400, right? At least today. All right, so my x is 400 feet, and we're done. Those are my dimensions. Now, what is the greatest possible area? How do you find the area? Length times width. What's my length? 400. What's my width? 200. Okay, so I would just multiply that out to get the area. And we have it. Okay, I have my shorter side, my longer side, and we have the area. Again, how do we do it? We know our area function is x times y because it's an area of a rectangle. These could be made, the x and the y could both be arbitrarily big. Make them millions or billions, you get a big area, which is silly, right? We really can't do that, so we use the constraint. We write out the constraint, the size added together have to total out to the amount of fencing. That allows you to isolate a letter, solve for one letter in terms of the other. Take that solution and plug it into the original equation. So instead of an x being here, we're replacing this x with the solution we found for x. So instead of x times y, it's 800 minus 2y times y. Once I distribute that y in there, I get a quadratic. I can rewrite my quadratic in a nicer way with the biggest power term first. I can see that it's a downward parabola, so I realize that the maximum will be at the vertex. So I need to find where my vertex is. How do I find the x of the vertex? This is really sort of the, I'll put this little y in quotes, this is really the input, or x value of the vertex, which we're calling y in this case, but it's the input value for the vertex. Okay, the input for the vertex is 200, negative b over 2a, and then the other variable, we would plug this 200 back into the constraint. The constraint relates the two variables to each other. Plug this 200 back in for x in the constraint, and you'll end up with y equals 400, or the other variable is 400. Okay? So my longer side in this case would be 400, my shorter side would be 200 in this particular example. And for my area, I would multiply them together, and I'm going to get what? About 80,000, I believe, right? If you multiply 200 times 400. Okay? So you should go ahead and be able to do your version of this problem. All right, let's go on to some more examples. Okay, this is problem 17, the evil supervillain. And so we've got a function here. Notice it's got a variable squared as the highest power, so that's a quadratic. The graph will therefore be a parabola. There's a negative leading coefficient, so it's a downward parabola. Okay, so what does a downward parabola look like? Looks like a downward parabola, right? So the notice the coordinates here, the output of this function represents the height. The input of the function represents the time. Okay, and so actually we're starting at a height of, when time is 0, we're starting at 245, at a height of 245. So the graph would probably, at time 0, if this is my time axis, when the time is 0, my height's 245. So we're actually starting right here. So it looks more like this. Okay, so this is not a very good example. This is a better picture. Notice, though, that the highest point, since it's a downward parabola, the highest point is going to occur at the vertex. So when they ask me for the time it takes to reach that maximum height, that's the time it takes to reach the vertex. So that's the input value, or x value, of the vertex. How do we find that? X equals what for a vertex? You should know. Okay? And you should be able to work it out with these numbers. What about the actual max height itself? That's the y value of the vertex. Okay, so once you get the x value or t value, the input value, you should be able to plug it back in and get the output value or height. Okay, so this should be a pretty simple problem at this point. If this is not a simple problem, go back and watch the part 1 and maybe even also the earlier parts of this part 2 video to help you out. Okay, it's really important stuff. All right, let's go to the next problem. Actually, I should for the numbers I have here, the answer I'm getting for the time needed is 8.878 seconds. And the value I'm getting for the maximum height is 631.173 meters. Okay, well, it already has the meters in there. I don't have to write that double. I don't have to write it twice. Okay, but anyway, these are the numbers I'm getting. These are the answers I'm getting with my particular version of the function. You'll get different numbers, but just in case you want to practice with my numbers first. Okay, all right, so now let's go to the next problem. Okay, so we're on problem 18 here, the last problem in this section. Notice I can rewrite this function as follows. I can rewrite this as y equals, think of this as negative 1 over 20,000 times x squared. I can pull the x squared to the right of the term. Think of it as 1 over 20,000 times x squared. Plus, I can think of this as 5 over 27 times x. I'm kind of pulling the x to the right of the term, minus 30. So what do you notice about this? What kind of function is it? Give you a clue. Starts with quad and ends with radic. How's that for a clue? Pretty good. Okay. Why is it quadratic? X squared is your biggest power. Okay, so this is a quadratic function. And so what do they want to know about it? They want to know, so first of all, what's the input, what's the output? if I graph it, is it a quadratic, is it a parabola opening upwards or downwards? Well, what's my leading coefficient? My leading coefficient is negative. So I have a negative leading coefficient. When you have a negative leading coefficient, that means you open downwards, right? So I have a downward parabola. What are the axes? Well, my input axis or horizontal axis is whatever the input is, and so x is the RPM. So my input is the RPM of the engine, how fast the engine's spinning or turning, okay? And what about the y? The y is whatever the output is. Y is the horsepower, okay? Notice when I put 0 in for x, I'm getting out negative 30. That's why I kind of drew it with a, so that when I'm at 0 on the x-axis or horizontal axis, I'm down in the negative region. Okay? So that's my y-intercept. Now, the next question is, where do we put out maximum horsepower? At what RPM? So when they say at what RPM, that means at what horizontal coordinate value? So what's the horizontal coordinate for the maximum, or for the vertex? So we know how to find vertexes, right? We know how to find the horizontal coordinate. X equals what? You should be able to find that. Okay, now in this case, your A, B, and C are a little bit weird, right? What are your A, B, and C? Your A is negative 1 over 20,000. Not a very pretty number. Okay, what about your B? Your B is positive 5 over 27. Also not a super pretty number. Okay, and then your C is negative 30. So that's your A, B, and C in this equation. And so you should now be able to find the input value of the vertex, which is the RPM that gives you the max horsepower. And then you should also be able to find the Y value of the vertex, which will represent the actual max horsepower itself. Okay? So you should be able to get these two results. Just think of it as a quadratic. Yeah, it's a quadratic with kind of ugly looking A, B, and C coefficients, but it is what it is. Okay? And you should be able to get this. This is an important problem. Okay? You have to be able to identify when you have an equation, if it's an x squared equation, that means it's quadratic. Pull the numbers out in front. So instead of 1x squared over negative 20,000, think of it as negative 1 over 20,000, all separate, times x squared. Instead of 5x over 27, think of it as 5 over 27 times x. Then it's clear what the coefficient is. Clear what the coefficient is. Okay? And that's it. You should be able to solve this. Okay? Now, in my particular example, the RPM that I'm getting for the max horsepower, the best RPM, is, in my case, 1851.852 RPM. Okay? 1,851 RPM. And what's the maximum horsepower? In my case, I'm getting 141.468. So I'm getting 141 horsepower at 1,800 RPM, which is actually pretty good. If you have an engine that gets max horsepower at such a low RPM, that's pretty cool. Okay? But that's a jet engine, though. It's not a car engine. All right? I'm not a jet engine expert, so maybe it's not that cool. But anyway, this is what it is. Okay? So you should be able to do this one. This one is an application of quadratic. Just peel off your numbers out in front of the x's so you can see what your A, your B, and your C are. Right? Take the 1 over 20,000 and kind of peel it off and bring it in the front as your A. Take the 5 over 27 and kind of peel it off in front to make your B. And that's my B, this is my A, and then of course the negative 30 by itself is your C. And that's it. Otherwise it's easy peasy, right? And there you go.